Hi everybody, welcome to this lecture on stacks. A stack is one of the most fundamental data structures that we're going to cover in this class. And stacks form the basis for many algorithms, in particular searching algorithms designed to output all the possible ways to visit nodes in a graph. And we haven't covered graphs yet. We're going to cover graphs later in the semester. And in between stacks and graphs, we have other sorts of data structures as well, which we're going to cover, including binary search trees and also hash tables. So stacks form the basis for a lot of the material that is yet to come. And we are going to look at the implementation of a stack in Java, which is the official language of this course. That may change in the future. And what we're looking at is the definition of a node class, which we can use to create a linked data structure. And in this circumstance, we're implementing a stack using a collection of nodes, and we have to define the node class in order to be able to build the stack. It is also possible to implement stacks using arrays. So if you've looked at the reading on stacks in Introduction to Algorithms, you'll find that the stack that's described there, does differ slightly from the implementation in Java that we'll look at later in these slides. But don't be concerned, because what that means is, that even though pseudocode describes an implementation in a specific way, if we have an understanding of the way the pseudocode works, we can also provide alternate implementations, which might even also provide some performance improvements. So here's a look at the stackEmpty method. You can see stackEmpty is a method that has a sol parameter, which is a stack. And in stackEmpty, we're testing to see if s.top is equal to 0. And if s.top is equal to 0, that means our array, our underlying array, has no elements in it, in which case we can say the stack is empty. And you can see if this circumstance arises, the test for equality between s.top and 0, if that evaluates to true, we're returning true. And that fits the semantics of the name we've picked for this method, stackEmpty. So stackEmpty is going to tell us if the stack is empty. And it's also going to tell us if the stack is not empty. So in the event that s.top is not equal to 0, we're in the else, and we're returning false, in which case we know the stack is not empty. And we also have a push method, which is used for adding keys to the stack. You can see push is defined as having two parameters, the stack, and also the key to push. And I just want to reemphasize the fact that the key, which is represented by x as the second parameter in push, is a unique natural number. So that means we're talking about 1, 2, 3, 4, 5, all the integers up to positive infinity that we could potentially use as a key. And the other thing also about the key is that it has to be unique. So we're never reusing the same key when we're using the stack. We're potentially pushing a variety of keys, each of which is unique. And each time we work with the stack, the same rule applies. Here in push, we have again the parameter s, which is a stack, and x, which is a key. And we're setting s.top equal to s.top plus 1. And then we're setting s.top equal to x. And this effectively stores x, the key that we're pushing. One thing you may notice here is we're not checking to make sure that we have enough memory. So if we don't have enough memory, then it doesn't make sense to do the push because that would presumably result in overflow, which might lead to runtime errors, and that is, of course, undesired. So a potential improvement here, and we may look at this in the lab, the second lab, which we'll be working on. We want to ideally be able to test to see if there's space for another key. And that's something that we can decide based upon the size of the underlying array. We also have a method for removing a key from the stack. You can see this method is called pop, which is a method that has a single parameter s, which is a stack. And we're immediately testing to see if the stack is empty. We rely upon one of the methods we've already implemented to determine whether or not the stack has keys in it or not. And if the stack is empty, we're outputting underflow, which means there are no keys to pop from the stack. Otherwise, we know that the stack has at least one element in it, and we're simply setting s.top to s.top less 1, and then we're returning s.top plus 1. This may seem a little odd how we're decreasing s.top here in the first statement in the else. Well, it's the only statement in the else. And then we're immediately adding 1 to s.top. There may be ways to improve this, and actually this is a good thing because it means there's potentially a more efficient way to do it than this pseudocode describes. So some simple stack operations. We have our stack in its initial state with a 15, a 6, a 2, and a 9. You can see the keys are in no particular order, and that's something to keep in mind. And you can see s.top is equal to 4, which is the subscript of the most recently pushed key, which is 9. And then between step A here and step B, we're pushing 17, and we're also pushing 3. And s.top ends up at 6. And then finally, we're popping the stack, we're removing the 3, and you can see s.top gets decremented to 5. And this is the first part of our implementation of a stack in Java. And in this slide, we're looking at an implementation of a node class in Java. You can see we have our class called node, and node has two attributes, an integer called key, and also a node called next, which is a reference. And we have a single constructor, which enables us to declare an instance of node with a specified key and also a specified next reference. Here you can see an implementation of a stack in Java. And you can see we have our class, which is our stack class. We also have our node reference to the top element. And that's the only reference we need to keep. That tells us where to push, and it also tells us where to pop. And you can see isEmpty is pretty straightforward. We're just returning top to see if it's equal to null. If top is equal to null, we're returning true. If top is not equal to null, we're returning false. And this will tell us whether the stack is empty or not. And we also have a public push method, and we're passing in this integer parameter k, and k is the key that we're pushing. Again, I just want to emphasize that we're talking about keys, which are unique. So in any one sort of implementation, we're only going to be using a given key a single time. 0 is not a valid key, and we're not talking about negative values either. We're just talking about positive integers like 1, 2, 3, 4, all the integers all the way up to positive infinity. And you can see in our push method, we're receiving the key, which is named k. We're allocating memory for an additional node. We're passing in k and top. Take a look back at the previous slide to see the implementation of our node class. And you can see we're calling this node constructor. We're passing in k, we're passing in n, and then we're simply initializing key to k and next to n. And all that happens right here, where we're allocating memory for an instance of node. Then we're setting top equal to temp. We still have our top, the old top. The new node points to the old top. We set top equal to temp because we have a new top. A stack is known as a last in, first out data structure, which means the most recently pushed key is the next to be removed or popped. And here in our pop method, you can see pop is a public method that returns an integer. If the stack is empty, we're returning -1, which of course is a sentinel value because remember that keys can't be negative, keys can't be 0. Keys are only the integers 1, 2, 3, 4, 5, all the way up to positive infinity. So when we return -1, we're telling the caller of the pop method that the stack is in fact empty. Otherwise, we're allocating memory for a key, a new, temporary key, which we're calling k, and we're setting that to top.key, and then we're simply setting top to top.next. So we're removing the reference to the old top, and then we're printing that we popped k off the stack, and then we're simply returning k. And here is implementation of a stack application in Java. And so this relies upon the class we just examined, the Java class we just examined. We're declaring an instance of stack called myStack. We're pushing 3 keys, and we're popping twice. And this is the console output of the stack application. And you can see 88 is pushed, 77 is pushed, 66 is pushed. And then we pop, and you can see the most recently inserted key or pushed key is the next to be removed. And that makes the stack a last in, first out data structure, which is sometimes represented as an acronym, LIFO, last in, first out, meaning that the most recently pushed key is the next to be popped.